So far we have discussed three different techniques for polynomial interpolation. We have seen that we can invert Vandermonde matrix, we may use Newton's interpolating polynomial, and we may also use Lagrange's interpolating polynomial. Now we'll see an example how to use Lagrange's polynomial. Recall that in Lagrange's polynomial, the coefficients are fxi, so they are readily available as soon as we have the data set. However, the basis functions are slightly complicated and you have to find them out. So let us see how to go about it. In Lagrange's polynomial, just like any other interpolation scheme, we need n+1 discrete data points to fit an nth degree polynomial, and then in Lagrange's case, Li is our basis function, fxi is the coefficient. A linear combination of this basis function will give us the polynomial. So let us take this example where y is a natural log of x and we want to fit a polynomial of degree 2 in this interval of 1, 6. Since the degree of the polynomial is 2, which means n equals 2 and n+1 is 3, that means we have 3 data point and we are taking this data point as I equals 0, 1, 2, 3 data point. So y equal to fx will be given by I equal to 0 to 2 sum of that Lix fxi, and if I break it down it will be L0x fx0, L1x fx1 and L2x fx2. We also know that Lix will be given by j equal to 0 to 2 here, x minus xj, xi minus xj, and j is not equal to I. Now we have to select the data points, 3 data points in the interval 1, 6. So what we do is that we take one data at xi equals 1, one as xi equals 6 and another in between. So I have taken here x equal to 4, slightly this side or that side will not matter much, but don't take this intermediate point close to any of these edges. Do not take close to 1 or close to 6. Now for xi equals 1, I have this function y equals ln x, so I can calculate this fxi. For 1 it is 0, for 4 it is 1.386, and for 6 it is 1.7917. So now we need this L0x, L1x and L2x. You see that fx0 is 0, so essentially L0x will have no contribution in y equals fx. So what we do is that we don't go for the calculation of L0x, we start from L1x, and we know that L1x will be given by this expression, that is product of x minus xj, xi minus xj, but j cannot be I. So in this case j cannot be 1, which means j can be either 0 or 2. So j is here and here. So first I take x0 and then I take x2 as j, and then I have to put xi, and I is 1 here, so I have x1 here and x1 here. Of course I have x here. So now this is the expression of L1x. I'll now take this value of x0, x1 and x2 from here. x0 is 1, x2 is 6 and x1 is 4. So when I plug this in, I get an expression x minus 1, x minus 6, 4 minus 1, 4 minus 6, which gives me minus 1 by 6, x minus 1, x minus 6. Similarly, I take L2x, here I equals 2. So when I take this expression, that product of x minus xj, xi minus xj, here I cannot be 2, j cannot be 2, so j can be either 0 or 1. So these are my j's here, and I equals 2, so I have 2 here and 2 here. Then I plug the value of x2, that is 6, x0, that is 1, and x1, that is 4 from here. So the expression comes x minus 1, x minus 4, and here I have 6 minus 1, 6 minus 4. So I have 1 by 10, x minus 1, x minus 4. So now that I have L1x and L2x, I already have f of x1, f of x2. So I can now go back to this expression and I can plug in L1x, fx1, L2x, fx2, which will give me this fx1 is 1.386 from here, and L1x is minus 1 upon 6, x minus 1, x minus 6. So I plug this in here. So this gives me the expression of fx now. So my interpolated polynomial is this, which we hope that it would be close to y equals ln x. Is this really close? How close it is? To check it, at least what you can do is that you can see a qualitative plot, and this is going to be the plot. Here you see that this black line is y equals ln x, and this red line is the polynomial interpolation of this. We have taken only 3 points. This is my x equal 1, this is x equals 4, and this is x equals 6. You can see that in all these 3 points, the interpolated curve cuts the actual curve y equals ln x. And in remaining part, it is slightly away from y equals ln x. But as you can see here that our approximation is not that bad. In fact, if we can take few more points, it may be better. We don't know that, but it could be better. That you can try by your own. Now that you have some idea how to apply Lagrange interpolation in a real problem, you can go ahead and you can do numerical experiments based on y equals ln x, y equals x ln x, and y equals x plus ln x, and in every case you fit a polynomial of degree 2, just like we did in this example. Already the first case you know the solution, so all you have to do is second and third case. Then you repeat the same example with Newton's polynomial, and then you think about it and comment which one is more advantageous here. I also urge you to plot all the functions along with their interpolated polynomials to see how well they are matching. That's all for this lecture. Thank you, and I'll see you in next class.